Over the past century, scientists have become deeply interested in the concept of black holes. The idea started gaining traction around 1916 and has grown into a major puzzle in astronomy. These strange phenomena in space are places where gravity is so intense that it warps reality. It just doesn't work like that. A black hole may be 2 to 4 million times heavier than our sun, yet it remains a big question mark despite numerous research efforts. We've gone from knowing next to nothing to determining some specifics, with constantly new discoveries emerging. Yakubu's most recent find includes surprising information about the contents of black holes that could alter our worldview, challenge what we thought we knew, and provide new ways of looking at these space objects. These new findings might lead to more investigations into potential aspects we missed. Come explore the fascinating world of black holes with us and see what secrets are concealed within the vast universe. So, what are black holes anyway? Before we dive into Yakubu's most recent activities, let's look at the fundamentals that most people have a common notion of. A black hole is a concept many are familiar with, but important details remain unclear. In 1916, Albert Einstein's theory of general relativity predicted that black holes should exist, but it was just an idea. It took about 50 years for anyone to find evidence that black holes are real objects in space. This happened during the 1960s when research on a star called X1, which was emitting X-rays, showed that those X-rays were moving in a systematic manner but were being sucked into something extremely dense and invisible. This object turned out to be a black hole, completely altering how we view space. It was a huge deal because it proved that black holes weren't just in Einstein's head, they were real and mysterious, so we had to investigate them further. More on this great group of scientists later. Everywhere, scientists began to attempt to learn everything they could about black holes. They found out that our galaxy alone could contain approximately 100 million black holes, but finding them is difficult, so that's just an estimate. Even though finding black holes is extremely challenging, scientists believe millions of them are concealing themselves in our galaxy, making it even more crucial to comprehend them. Let's discuss how gravity works in black holes. The gravity of black holes is so immense that anything that comes too close is crushed into a tiny point known as a singularity, where the laws of physics no longer apply. In essence, black holes resemble enormous vacuum cleaners in space, sucking everything up. One of the most terrifying aspects is what happens when you fall into a black hole. You'd get stretched out and turned into a singularity. Your body would be torn apart by the intense gravity before you were destroyed, so it's best to stay far away. Despite the fact that they are scattered throughout the universe, the nearest black hole is about 500 light-years away, which is a little alarming. In 2021, researchers achieved something remarkable and captured the first clear picture of a black hole, the M87 black hole. This required taking numerous images and combining them to create a single picture. As they gathered more information, the researchers realized that black holes have 3 layers, even though people often think they're just empty voids. The first layer is called the event horizon, the point where, if something crosses, nothing can escape. Once it crosses that line, it's gone. The second layer is the photon sphere, where gravity is so formidable that it prevents light from escaping. Finally, there's the singularity, where everything gets crushed into a tiny point, and reality and all its laws break down. What's even cooler is that every black hole is different. They all have those 3 layers, but they are defined by their distinctive behaviors. They are difficult to study because our usual scientific methods don't work. Scientists have to examine them indirectly by analyzing the radiation they emit or the gas and dust surrounding them. You can't just send a probe into a black hole because anything that crosses the event horizon will be pulled into the singularity and destroyed. So there's no point in wasting billions on probes that won't return any useful data. That means researchers have to study black holes in 2 dimensions, even though they are really 3-dimensional, making things even trickier. No 2 black holes are the same, so when we study them, we have to keep in mind that our understanding of physics applies differently. Theories suggest that black holes might form when massive stars collapse. When a star runs out of fuel, it can't fight against its own gravity, so it collapses into a black hole if the star is large enough. This process continues until everything becomes a singularity. To discover more about black holes, NASA scientists looked at the center of the universe, especially the M87 galaxy. They observed a huge swirl of hydrogen gas spinning very quickly, at about 1.2 million meters per second. That gas would typically split apart due to centrifugal force, but it remained together, indicating there was something massive in the middle, probably a black hole. Researchers estimate it is about 3 billion times heavier than our Sun. Another fascinating idea came from a New Zealand mathematician named Roy Kerr in 1963. He used Einstein's equations to describe how rotating black holes behave. He stated that, rather than collapsing into a point, a rotating black hole forms a thin sphere, referred to as a ring, which is spinning. This ring of material is critical for understanding how physics breaks down near black holes. Kerr's idea also suggested the possibility of an Einstein-Rosen bridge, which is like a wormhole that could allow travel through space-time to connect distant regions of space or even other universes. To understand wormholes, you need to know about space-time, which, according to Einstein's theory, is like a four-dimensional fabric that gets bent by heavy objects. This bending creates gravity, which affects how other objects move. Think of space-time like a piece of paper. When you fold it, you create a shortcut between 2 points. That shortcut is a wormhole, allowing travel through space to connect far off, places almost instantly. Wormholes are just theoretical, and we haven't found any proof they exist, but they are a natural outcome of general relativity. The thing about wormholes is that they would likely collapse if they were unstable. The concept of using wormholes to travel to different parts of the universe, or even through time, has fascinated physicists for years. One kind of wormhole, called the Kerr wormhole, has been especially interesting. It's named after Roy Kerr and is a hypothetical wormhole that could connect two distant points, possibly even different universes or timelines. It would be incredible to use wormholes for interstellar travel or time travel, but there are significant challenges. For one, wormholes are thought to be unstable, and the radiation and forces around them would make it nearly impossible to travel through them safely. Some argue that Einstein's equations are useful for understanding gravity, but don't explain the controlling quantum forces, radiation, and microscopic particles. To truly understand wormholes and black holes, we need a new theory that combines gravity with quantum mechanics. This theory of everything is something that many physicists, including Jacobi, have been working on for years. A promising candidate is superstring theory, which posits that subatomic particles are actually tiny vibrating strings. These strings make up the universe's fabric and could explain not just gravity, but also what happens around black holes and wormholes. However, superstring theory also requires additional dimensions of space that are so small we can't detect them with current technology. Even with these challenges, attempting to comprehend black holes, wormholes, and space-time keeps scientists captivated, and it may lead to discoveries that change how we see the universe. Continuing from where we left off, the search for superstring theory and other theories that seek to unify the forces of nature remains a formidable challenge. However, it might provide us with some insights into the way reality works. These hypotheses assert that there is more to the universe than just the 3 dimensions of time as well as space. We are aware that additional dimensions may exist, but they're so small that we can't see them with our technology. But those dimensions may hold the key to comprehending phenomena like black holes, space's wormholes, and other mysteries. The superstring theory provides us with a cool illustration of the universe, declaring that forces and matter are distinct forms of tiny vibrating strings. These strings' rate of vibration varies, and each vibration makes a different particle, like how a guitar string can make a variety of sounds based on how it vibrates. The basic particles of nature might be different vibrations of superstrings. If this is true, it would not only give us one explanation for the fundamental natural forces like gravity, the strong nuclear force, electromagnetism, and the weak nuclear force, but also provide us with a fresh understanding of how the universe is built. This could answer some big questions in physics, like what dark matter and dark energy are made of. These things make up most of the mass and energy of the universe, but we don't know much about them. Still, superstring theory hasn't been proven. Yet. One problem is that the extra dimensions it talks about are so tiny that we can't see them. To see these dimensions, we'd need supersensitive instruments, and even then, the evidence might be hard to observe. This complicates superstring theory testing using standard methods of science, but the theory is beautiful and logical, resulting in it being one of the most interesting ideas in physics. At the same time, scientists are looking for new approaches to comprehend black holes. For instance, quantum gravity is a field that tries to combine quantum mechanics to provide an explanation of how general interactions between microscopic relativity, which explains how big things like planets and stars act. The goal is that, by combining these two theories, we can understand how gravity works on a tiny scale and learn more about black holes and other features of space where quantum mechanics and the theory of general relativity are crucial. When studying black holes near a black hole's event horizon, where gravity is extremely robust, we require a theory that explains both quantum and relativistic effects. In fact, the inside of a black hole, where the singularity is one of the most bizarre locations in the universe. A point is the singularity, where space and time get so warped that the usual laws of physics stop working. To understand what's happening there, we need a theory that can combine quantum mechanics and general relativity. That's why people are working on ideas like loop quantum gravity and other quantum gravity models, which try to fix these problems and give us a better picture of black holes. As we keep trying to figure out black holes, one thing is for sure. The more we learn, the more we realize how much there is to learn. Black holes aren't just points of destruction, but also regions, with complexity and the possibility of being entry points to other dimensions, or the key to comprehending black holes in space and time. They are extremely significant to study. As our methods and theories improve, so will our understanding of these mysterious objects. Looking ahead, the next big thing will be to improve how we observe and investigate one of the black holes. 1. Of the coolest things that's happened recently is the development of gravitational wave astronomy. Gravitational waves are ripples in spacetime that are caused by big objects moving around, like when black holes merge. By finding and studying these waves, scientists can learn about black holes and other things in space in ways we couldn't before. Gravitational wave detection has already given us some big insights into how black holes merge, and future experiments will most likely reveal even more. Another good area to focus on is using advanced telescopes and imaging, like the EHT, or Event Horizon Telescope, which took the first picture of a black hole in the M87 galaxy. This shows how new technology can shed some light on black holes. By combining information from many radio telescopes around the world, the EHT was able to capture the black hole's shadow, giving us a look at one of the most enigmatic items in the universe.